Hello, this is video 2 of the series of videos on semi-confined flow. In video 1 we derived the differential equation for the head in the aquifer. The second derivative of the head with respect to x squared is equal to h minus h star divided by lambda squared. And we're going to make one more modification. We would like to have on the left the second derivative of h minus h star, since we also have h minus h star on the right. And that's fairly easy to do if we can state that h star is constant. H star is the water level above the leaky layer, and it's easy to pick that constant, so let's do that. So we have a modified differential equation, the second derivative of h minus h star with respect to x squared is equal to h minus h star divided by lambda squared. And this differential equation, we made the approximation that h star is constant. This differential equation actually has a name. It's called the modified Helmholtz equation. And we can solve it. Let's first try to find an equation for a general solution to this differential equation. And the differential equation isn't so bad, because what we see is that the second derivative of h minus h star is equal to h minus h star itself divided by a factor, lambda squared. So what function do we know that if you take the second derivative, you get the function back, maybe times a constant? I think that would be an exponential function. So let's try and find a solution. We're going to find a solution for h minus h star. Let's say we find a solution in the form c, a constant, times e to the power ax. And we don't know yet what capital C is, and we don't know yet what small a is, but let's see if this would work. Well, how would we find out if this solution actually is a solution to the differential equation? We have to take derivatives and then substitute it in a differential equation. So the first derivative, this derivative dh minus h star dx, we take the derivative of c times e to the power ax, that becomes c times a times e to the power ax. And we can do that again. We can take the second derivative of h minus h star with respect to x squared. So we differentiate one more time. We get another small a in front. It is c times a squared e to the power ax. And we can substitute that into the differential equation. The differential equation is written here on top, so we substitute that in. The second derivative, shown here in pink, is c times a squared times e to the power ax, and that should be equal to h minus h star, which we have guessed to be c times e to the power ax, divided by lambda squared. And now a lot of things are going to cancel. First of all, and most importantly, the exponential function cancels. So apparently we picked the right function. We're not really surprised, we kind of knew that would happen. But also, the capital C is canceling. So we could have picked any capital C and it would have worked. And then we are left with one equation. A squared is 1 over lambda squared. That means that a should equal 1 over lambda. Or a should be minus 1 over lambda. Either way, it works. So it turns out we have two values of small a, and this general solution can now be written as the head is equal to either e to the power minus x over lambda, right? That is when small a is equal to minus 1 over lambda, or it is equal to plus x over lambda, or any linear combination of the two, because we could have picked that capital C any way we wanted. So let's call those two coefficients capital A and capital B. This is the general solution to the differential equation shown in the upper right hand corner. And now of course we can solve a problem. Let's try to solve one. Say we have semi-confined flow from a canal into a polar area. So we have an impermeable bottom layer, we have a semi-confining layer right here, we have a dam, and we have a canal, and the canal cuts all the way through the aquifer. That's why I'm showing the dashed line. This is all water. Or maybe I should have used a different color. How about blue? Here we have water, and in the polar, the water level is fixed right at the surface, H star. What will happen is that the head in the aquifer, which I'm going to draw with a different color, blue, right at the canal, the head in the aquifer is going to be equal to the water level in the canal, H0. Then if we go farther into the polar and we figure out what the head is, then the head will slowly decrease to H star. And if you're far away from the canal, then the water level in the aquifer will be the same as the water level above the leaky layer and equal to H star. So anywhere where you would cut a, let me see if I can draw a very small little observation well. If we cut an observation well right through here, there we go. If you cut an observation well through here, and let's fill the leaky layer back up right here, so looks a little nicer, and zoom back out. If you cut an observation well through the leaky layer, then the water level in that observation well is right where I'm drawing that line of the head. This is the head as a function of x. Which reminds me, this solution I've written above here, I forgot one little term. I should do that because the solution we derived was not for the head, but for the head minus H star. So let's modify that. This was derived as H minus H star. There we go. Much better. And we are trying to solve this problem. We have to figure out, or define somewhere where the coordinate system's origin is. So let's say that is right at the boundary. Then we have our problem defined here physically. Now we have to define it mathematically. We need to find two boundary conditions. Our differential equation here in the upper right-hand corner is a second order ordinary differential equation, which means that we're going to need two boundary conditions. And you can also see that from the general solution. The general solution has two constants, capital A and capital B. So we need two conditions. Let me see what we have. Well, right at x equals 0, we know what the head is. The head is equal to H0. And if we go far to the right, when x goes to infinity, then the head is equal to H star. And we can also define that then into H minus H star. So H minus H star at x equals 0 is H0 minus H star. And H minus H star for an x becomes very large, becomes 0. Now we have to use those two conditions to solve for capital A and capital B. And we'll start out with the second one. If x becomes very large, then we get capital A times e to the power, so we're looking at this term now, capital A times e to the power minus infinity. Well, e to the power minus infinity is 0, so that term becomes 0. The second term, this one, if x approaches infinity, we get e to the power infinity. That becomes infinitely large. Yet we want that h minus h star is 0. And the only way we can do that is when b is equal to 0. All right, that means that we have only one constant left. We can use the second condition to solve for that. H at x equals 0 minus h star is equal to a times e to the power minus x over lambda, but x is equal to 0, so it's equal to a is equal to h0 minus h star, because that was the condition we tried to apply. Right? So we have our final solution. The head as a function of x, the head minus h star, h minus h star is equal to capital A, h0 minus h star, times e to the power minus x over lambda. Or if you wish, h is equal to h star plus h0 minus h star times e to the power minus x over lambda.